We live in a world of possibilities and probabilities. From a simple toss of the coin or a simple roll of the die to volatility in stock markets, fluctuation stands everywhere. By the end of today's lecture, we will be able to understand the nuances and concepts associated with normal probability distribution. So, we'll head or progress in a structured manner, like I've been doing in my previous lectures. So, we'll be discussing the definitions. These are the things that we teachers or students they normally are averse to or they skip. We'll understand the concepts and, of course, any topic, whether it be geography or statistics, is incomplete without its application. So the we'll do some numericals associated which have been asked in the exams like UGC NET in the graduation and post graduation geography exams, and it will help you somewhere or another down the way in life. Okay. So first, when we discuss about the definitions, so first of all, what exactly is probability? Okay. So probability, the chance, it measures the chance of an event to occur. Okay. The general expression or the general notation which we use in mathematics or statistics is Px. Here, P stands for probability and X is the chance of a particular event to happen is equal to number of favorable outcomes for X upon total number of outcomes. Okay, there is a reason why I am starting with the basic. What is a probability? Okay, so this is probability is done. Now, since we are going to discuss about normal probability distribution, it is going to be easy for you to understand if I segregate the three terms. We've understood probability. Now we combine probability with distribution. So probability, if we, so what is probability distribution? Basically, it is a mathematical function which shows the values a random variable can take and the possibility or the probability, the chance of those various random values of occurring. Okay, so two things are important. One is in the previous slide, in the when I told you the definition of probability, we were talking about something specific. Okay, in this mathematical function, the distribution, a random variable, suppose x or y, it can take many values, and probability of those values is given by probability distribution. Now we attach normal with it. Okay, normal distribution in simple words, it is a continuous bell-shaped symmetric curve. Okay, so there are various types of probability distribution. We are going to focus today on only one of them, which is normal probability distribution. It is used for continuous values, like we can say mark or height of students, rainfall. Okay, so we'll be dealing with few examples also. A continuous variation. Fine. So other important things that we need to discuss is the some basic stuff like mean. This will be used. Okay, so what is mean? It is the average of the sum of observations. Okay, so if we mean is normally denoted by mu, so it is the sum of observations upon n, number of observations. Okay, then we come to standard deviation. What is standard deviation? If we can easily write the formula. So sd, or this sigma, is equal to square root of of so square root of the mean of the sum of the squared deviations. Okay, so this is how we express this. But what is the definition of standard deviation? It is the variability. It showcases the variability in the data values. How the various values in a particular data sample, they are spread away from each other. For example, if we consider a set of marks, the students, so let us say that mu in that case is 60. Then some of the students, they are scoring my marks like 30, then 70, then 20, 10, 90. Okay, so consider this value, then consider this more closer to 40, like 40, 50, 55, 65, 70. So when we calculate the standard deviation sigma for this set of values with same mean, here mu 60, here also mu is 60, so here sd will be larger, which indicates the larger spread of the values from the mean. Here it will be smaller. The spread or variability of raw data is small. Okay, then we come to Z-score. First, we understand standardization. So, standardization, basically, we are trying to reduce a variable to a normal standard scale so as to reduce the dependence on units, to make a variable, to make us be able to make a variable possible to compare across various other types. Okay, so what we do is we use the Z-score for standardization. A simple example of standardization, normally, like you any exam, like a multi-subject exam, a multidisciplinary exam like UGC NET. So there are various subjects in this, like geography, history, commerce, anthropology. So in this, the levels and the concepts are different. So for the difficulty levels are different. So a standardization score. So if geography paper is very difficult in 1 year, so they use a standardization or some technique to bring it to par so that the marks of the students of various subjects, they can be compared to one another. Okay, so Z score. So Z score, again, the formula is x minus mu upon sigma, but we are not going to discuss only the formula. Basically, while standardization or using Z score, what are we doing is we are reducing the mean or mu to 0 and standard deviation to 1. What does that mean? Remember, in our previous example, we took the value of 60 mu. This is the actual value. Now, suppose we have to compare this value or this marks in one subject with student scoring marks in another subject. So we need to, if this is for geography and another is for mathematics, and here the mean is 70, so we reduce both means to a standard normal scale to enable apt or commensurate comparison. Okay, so this is the okay. So here what is this means is that deviation we have already discussed. Standard deviation, what it means in this case, since mu is 0, it gives the understanding or impression that the values or the variations in the data are differentiating or distinguishing between one another in units of 1. So they can be 1 or -1, -2. Values can be anything. Marks can, normally marks are not negative, so they can be 10, 60. They are always positive. But if we take the mu 60 as 0, then marks less than 60 will fall along the negative line of the z-score, and marks more than 60 will fall along the positive line. This is the concept. This is important. Okay. Then one important concept, because these are, you can link all these further. These are useful. So you have to know this H naught or null hypothesis. This you have come across, might have come across as in various texts. So null hypothesis, the definition is that it is the hypothesis which shows that there is no relation or difference or significance between a sample population. Okay, sample population, I mean, like we have a raw data, like we have a group of students. In the previous example, we take raw data sample from the population of students, and so this is the null hypothesis. Why I am discussing it right now, just the concept, because we have to discuss this, the p value, which is almost everything is going to revolve around this, the future test, statistics t test, the z test, the chi-square test, then man Whitney U. Okay, so all this p value. So p value, what is the actual definition? So the p value is the probability. It's again a type of probability, not the probability itself. The of a variable, probability of a variable to assume a value as extreme as the statistics which we get from the null hypothesis. Okay. So what is this? If we denote it or try to denote it by the mathematical expression, so P is equal to P x, where the hypothesis is H naught. Okay, we'll discuss this when we discuss the normal distribution curve. So when, if I just draw the normal distribution curve here, okay, so the main properties of the curve I've already told you. It is symmetrical, bell-shaped, symmetrical about an imaginary axis. Okay, normal distribution is there. So for example, there are two. Now we are going to get into the thick of things. So just pay attention. P value and Z value. Okay, we are going to alternate between these two. So for example, this is the standard normal curve. Whenever I use the word standard, this implies that we are not dealing with actual values, we are actually dealing with z-scores or the normalized, the standard normalized scores. So for example, we are doing some calculation, we get a z value suppose you can say zero point 0.9. Okay, then corresponding to that z value, you will get a p value. Okay, I'll explain to this when we discuss the tables. So suppose p value comes out to be 0.01. So what is the p, the probability this p comes to? So the p value in this case is this shaded area. Okay, and in two-tailed case, in the two-tailed observation, here also there will be a p value. So this is actually the p value. It is the area of the shaded region which indicates a value as extreme as that taken of a test statistic in case of null hypothesis. Now, it is very confusing, I know. So, a simple example. Suppose that we have been given a mean of a particular population, mean of the height of a particular population, say 170 meters. The standard deviation is given. Okay. Now we take a random sample of 100 people among them. Okay, and we find that the mean of those 100 people, the mean of the heights of those 100 people comes out to be 174. Now we have to test the hypothesis that the mean height 170 lies in between in the confidence interval. We'll be discussing these concepts further. I'm just mentioning it. So just try to focus on the important things, which will be which I'll use when we discuss this topic further. Okay, so here I am trying to explain the p-value. Now, for 170, we have to test this hypothesis, that null hypothesis say that the z value, the p value corresponding to this, it will lie in between this. It is, we fail to reject the hypothesis. So when we take out the p value, suppose the confidence interval we can say is 90% or zero point 0.01 in this case. So if the p value from this hypothesis testing, it comes out to be less than 0.01, that is 0.0003. Okay, so it means it lies in the extremities. Okay, and thus the hypothesis that there is no difference or relationship between the heights of the population, that is rejected. If it is greater than 0.01, it comes out to be 0.9 or 0.8, then we say that we fail to reject the hypothesis. So what I mean to say is the p-value is actually the area in the extremities. Sometimes we call it also the two-tailed p-test. Okay. I know it might be confusing if you're reading this for the first time, because concepts, even I had to study it again and again to get a hold on this concept. Okay, but right now this is important from the point of view what is p value. It is not exactly probability. It is the area. Here, when we talk about the normal distribution curve, we talk in terms of probability as displaying the area, not a particular number or value itself. Okay. Few more notations and concepts, because in books what happens is all these notations, the symbols, alpha, p, phi, they get confused, they get lost in translation. So the clarification is very important. Okay. So first of all, we have fx. What is this? Fx is basically a function, mathematical function, which explains or denotes the probability distribution, the normal probability distribution. Okay. Then, for example, like I draw this curve. So here, when we are taking the normal values, like we were discussing about the marks. So if we take 40, 50, 60, all these actual values on the x-axis, then this curve is known as the normal probability distribution curve. Okay. Then we have the phi. Phi, this is z. So phi z, as you can see, now we have standardized the values, and we are, the x-axis show the z-scores or the z values. So here we know that 0, then 1, 2, because we know that mean is reduced to 0 in the normal, in the standard distribution curve, and the deviations, they increase in step of 1. Fine. So here the function is known as the phi z. This is known as the probability distribution function, the standardized probability distribution function. Okay. Then finally, we have the cumulative distribution function. This is the thing which we are mainly going to talk about. So, cumulative distribution function, when we talk about, it gives us the area lying before a particular z value. For example, if we take the z value like this, so if we write, okay, so cumulative probability distribution phi z. So when we write this, not p, but this is capital P, the probability statement. The P like Z. So if I write this pi Z, it means that we are going to find the probability or the probability area for values lying below Z. So if we have to find out phi Z or probability area less than 2, so we will be considering this entire shaded portion from minus infinity to 2. So this is the expression. So I know a lot of concepts, but now the interesting part when we start discussing the examples and why the means of graphs and tables when we discuss, it will be absolutely clear. Okay. So this is the two-tailed p-value like I have been repeating time and again. Okay. So p-value, like you can see, what we do in general hypothesis is that we test the hypothesis, we come up with a z-score, then for the corresponding z-score, we find the p-value. And p-value, for example, if this is an example given in this graph, if z-score comes out to be 5, so the p-value corresponding to this z-value will denote this area. And if we are calculating two-tailed, that is negative and positive deviation, so this is two-tailed p area. Fine. But at the same time, if we want to know the cumulative probability distribution at for z equal to 5, then we will calculate this entire area from minus infinity to 5. So are you understanding the difference? This is why I am hell-bent or I am repeating the concepts from scratch, even though they are tough for me to explain itself. So p-value is also a type of probability, but it shows the area of the extremities. This cumulative distribution function, it is sort of an integration of this function up till the z value. Further clarification when we discuss numericals. Now, okay. Now we are going to discuss p in terms of p and z. Forget the p value. We are going to discuss the capital P, that is the cumulative distribution function p. For example, here, first of all, you see this. So this graph is giving us, is showing us the difference between P and Z scores. Now you can see, as I've been again and again repeating, Z scores, for example, this here we have 0. Then we have some particular values which we have taken. Why we have taken, I'll just tell you. So 1.65, 1.96, 2.58. Similarly, the negative values and corresponding p values 0.10, 0.05, 0.01. Okay. So basically, like I told you about the null hypothesis, H naught. So for particular z, suppose we say that the critical value is we have to take is that z is equal to 1.96. Okay, critical value. Or we have to say that we have to attain a confidence interval of 95% for saying that we fail to reject HO. We cannot say that we accept an HO because we are just taking a sample population. So it cannot be an exact, appropriate, or right. Okay. So now for we have 95%, if you convert it. So it's 0.95. Okay. And if you subtract 100 or 1, it gets 0.05. So 0.05. Now I'm just giving an example of what the p value aims, or what is the use of p value. So first we take a hypothesis like we did in the case of the height, various heights of the 170-meter height parameter. Okay, so we calculate the corresponding z value for this, z value for that. Okay, so suppose it comes out to be 1 point, we can say 1.65. Okay, the corresponding p value will be 0.10. So it will lie here, it will lie in this area. If we take the two-tailed p-test, the two-tailed p-test, okay, two-tailed p-value. So since the hypothetical statistic or the z-value calculated is lying in this area, so we say that we fail to reject the hypothesis. But if the p-value, it comes out less than 0.05, for example 0.003, then we can say that the hypothesis is rejected. Okay. So as we discuss, as you will come across various tests, you will further understand the use of this p-value. Now the next important thing is this. Okay. Now, sometimes what happens is, if in the numericals, or since I said that we are going to discuss the relation between the probability distribution, or the P, the capital P, and the Z values. Sometimes what happens is that the conversion is not easy, because I told you that the probability distribution function is the integration of the integration of the function of the fz, of the function, this graph. Okay, so sometimes it is easier if you remember the area, some numerical values. Will come to that. Now what happens is this 68, 95, 99.7 rule. So we can take this is actually 1, z is equal to 1, 2, then 3, then -1, -2, -3. This exact question from this concept was asked in UGC NET this year in December 2025, January 2026 session. So the area covered between z is equal to -1 and z is equal to +1 is 68.27, or you can approximate it to 68%. That means that if we this probability distribution function, this graph represents any function of values of whose probabilities are being measured, then 68% of the values will fall between 1, -1, and 1. There is a logic behind it also. Just see the graph. If we take this as the midpoint, mean, why is this the mean? The mean, because it is a measure that most of the values will be clustered around it. Okay. So if the mean would shift towards right or left, so the majority of the values will also shift towards it. So that is why it is symmetric. As we go to this blue region, we can see that the area, the shaded part, the blue part, it also decreases. That means the probability of values lying between these two areas is shown by less area, so the probability becomes less, even lesser as we go further away from the mean. So this is the main concept. So this you can remember 68, 95 and 99.7. We'll discuss its application. Okay, first this was the question asked in UGC NET. So you can directly have a look at this. So it is very simple if we know or remember the 68, 95 and 99.7 rule. So here we have the z values and we have to match the probability. So standard, normal, variate, we know the z-scores, and probability, the cumulative probability distribution, the area. Okay. So although I remember the values, but still for demonstration. So this is 1, sigma 1, then 0, 1, minus 2, 2, 3, minus 3. Now, first see this value, minus 1 to 1. It is clear we can match this. 68, we have already discussed from the previous diagram. 68% straightforward. Okay. Then minus infinity to 0. Why is this 0.5? Now just try to extrapolate the information that you have gathered. See, this is the mean. This is the standardized normal values. So 50% of the values will lie on the right hand side of 0, 50% of the values will lie on the left hand side. So minus infinity to 0, the area will be 50%. If we this all of this area, if I say that this is 100%, so left of mu equal to 0, we have 50%, 50%. So minus infinity to 0 is 50%. This is also gone. Okay. Now, in simple various examinations, we can eliminate the options also. So A3, C1. Okay. So actually 2 can be, so there is these both are. So one option more we need to consider it. So we are left with minus infinity. We can check this, minus infinity to Z minus 1. So how will we get this? Okay. How will we get this? So again, just relax, calm down. We already know that this is 50% or 0.5 probability. We are talking in terms of probability equal to area. And this was 68%. So this half will be 34%. Okay. 68. Okay. 68 minus this 50 minus 34 gives us 16 or 0.6. Okay. So last this D will be equal to 2. So this is the option. If you want to check this just for greater clarification, you can check this also. So this minus 1 to plus 2, how to calculate this? This is also beneficial because this can be asked. So here also minus 1 to plus 2, we have to calculate this area. So minus 1 to 1, we know it is 68. Now, how will you calculate this? Again, we have not calculated it till now. So what to do? So we know that minus 2 to 2, the 68, 95, 99. It is 95. If we subtract 68 from 95, what do we get? We get 27. And 27 will again be divided into two halves. So 13.5 and 13.5. So the area from minus 1 to plus 2 will be 68 plus 13.5, approximately 82%, 0.82. This might sound complicated, but if you just think about it, it is very easy. Just subtraction, addition, and figuring out where what lies where. Okay. Okay, so this is clear. One application is clear. Now we come to this. Now this is the main thing. If you don't have a scientific calculator also you need to have the advanced one. If you want to calculate this phi z or the cumulative probability distribution exact function. So phi z actually, the precise definition of phi z is that it gives the area from, like I said, if this is the z value, we have to calculate phi z, or we can take, suppose this is 2, so phi 2, it gives the area or the probability from minus infinity to 2. But you have to be careful with the table and its corresponding criteria of giving the values or the area which is covered for the corresponding z or the p value. Now check here what is important. Now you can see here, this is the same table given in your books also. Mostly these type of tables are given, but you have to, this z here, what is happening is, it has taken the example of 1.25. Okay. And 1.25, it has given, if we locate this 1.2 and we go to 5.3944. Okay. Now, phi z by definition should have been this whole area. Okay. But here the criteria is different. So here, what is this z score? So it is given, what is it? It is giving is that z, it is giving from 0 to z value. Okay, for example, here z is 1.25. So it is giving the area only this. So can you tell me that if we have to calculate phi z, actually we have to calculate the entire area. So what we'll do? Simple, we have this area, we'll add 0.5 or 50%. Left of the z equal to 0, we have the 50%. So similar concept is there. Some values also, if you can remember, if z table is not available or not given, or you don't have access to a scientific calculator, even the scientific calculator that I have, it can easily convert the z score to the probability area, but the inverse is not possible. It is difficult. So sometimes these values, this inverse, if z table is given and you know the z value, you can easily do this like we have given an example. But if p value is given or the area value is given, then the inverse, to calculate z score from the area, the left tail, it becomes difficult. So some values, if you can remember, it is good. I'll also talk about an example numerical given in the book, also asked in the exam. So z score is 0. So this means area left tail. Now we are talking about, if I draw the graph here itself. So if z is equal to 0, so phi z, we are talking about phi z, or phi z 0, or we can say p z less than 0. So we know that it is 0.5 or 50%. Easy. Then 0.674, it will lie somewhere here. We have not, this is not part of that 68, 95, 99.7 rule. So we need to remember some of the values. So this indicates that this area is 75%, or probability is 0.75. Then as we go 1.282, so this keeps on increasing. If you remember these values, they also correspond to the p value, or you'll come across them in the further tests like t test and others are such tests, statistical tests, which include the null hypothesis. Okay. Now finally the interesting part. I hope you are still there with me till this time, because now we have actually arrived at the application. This is the interesting part. So 60, standard deviation 12, interval of marks covering around 99.73. Okay, so when you see this, immediately you can see, so what is the, find the interval of marks covering around 99.73. So we know that the interval of marks will correspond to which values? Z is equal to -3 and Z is equal to +3. Now we can use the formula which was the Z-score is equal to x minus mu upon sigma. So average mass is 60. So mu is 60. So here we can put 60 and we have to calculate. X is the actual value of the marks. Okay. Here is the concept which I have taught, which I have discussed with you. Here you will understand what is actually meant by this. This X which we have found, which we will find out, actually we use this X to plot this Z-score graph or the standard probability distribution function graph. Now we are going to use these Z values to find out the exact marks. Okay, I hope now the concept is clear. Standard deviation is 12 and Z once we take +3, once we take -3. So X will come out to be uh, 60 plus minus 36. I hope you can do the math easily. So the interval will come out to be 96 and 24. So the actual values, the X values corresponding to this standard probability distribution function will be 24 and 96. So we have got the first part, find the interval. So the students, 99.73% of the students have scored marks between 24 and 96. Okay, now you can understand. Also give the percentage of students getting marks greater than equal to mean minus 2 SG. Okay, just forget this. Okay, mean minus, just let's do from the graph. So mean minus 2 SG is, so we have to, this is mean minus 2. So we have to now find this area. Is this easy or not? Because -2, we know that, again, to avoid confusion, this was -1, 1. So we had calculate this early, 34, 34. This is 13.5. And we have to calculate the percentage greater than this. So if we take this whole as 50%, we add 34 to it. This gives us 84 plus we get 13.5. Okay. So approximately 97.5% of the students, they have scored marks greater than this. So 60 minus, basically we can say 60 minus 24, 36. So percentage of students which have scored marks between 24 and 96, we have 99.73. Percentage of students which have scored marks greater than 36, we have come to this 97.5. Okay. So this is the easy application. Average height of students 5.3. So this is mu. Standard deviation sigma 0.6. Selection of 100 students. How many of them expected to be height more than 6 feet? So again, to make it clear, I'll draw a probability distribution function graph. Okay. So just to visualize, this is actually the normal, not the standardized one. Okay. We are going to standardize to set a normal standard scale to make things easy. So when we, so here we have to share, the threshold is 6 feet. So we'll convert this 6 feet, we'll reduce this 5.3 to mu is equal to 0, the mean to 0, and similarly this to the Z-score, the standardized score. So for 6, the Z will be again x minus mu upon sigma, which will be equal to 6 minus 5.3 upon 0.6. So this will come to 0.7 upon 0.6. This will come out to be 1.166, or we can say 1.17. Now this is the Z value. Now we have to calculate how many of them are expected. Okay. So first we'll calculate the percentage of values. Okay. So this Z-score is coming out to be 1.17, which corresponds to a height of 6 feet. We have to find first the percentage of students which have a height greater than Z is equal to 1.17. So we have to find this area. Now, even from the values which I discussed, to remember this area is not available. So now we'll take the help of the either the scientific calculator or the Z table. So p value for Z equal to 1.17. So this is 1.1, and then we go to 7. Okay. So 0.3790. Okay. But this is not the complete answer right now, because according to this table, this is the area. So if I try to explain you further, so what 37.90 is showing, it is actually this area. Okay. We have to find this area. So how to go about it? So we can simply, this whole area we know is 50%. We can subtract 37.9 from it. It will give us 12.1%. We get 12.1%. So 12.1% of the students have a height greater than 6. But this is the percentage. We have to find out how the number of students which have a height greater than 6 feet. So 12%, 12.1% of 100 gives us 12.1. Since 12.1 students are not possible, so we approximate it to 12 students. So that is the answer. Fine. Okay. The mean income of workers in a locality 5,000 per month, standard deviation 2,000, normally distributed, ninth decile. Now be don't fear if a new concept has come up. Just try to although even I was afraid when I was solving such question for the first time. So don't worry. Actually, the question is incomplete. It was actually estimate the ninth decile. So we have to calculate the income which is less than ninth decile. When we talk about ninth decile, we can also say that it is equal to the 90th percentile. What does that mean? Like we have percentile in a lot of competitive examinations, CAT, UGC NET, and other GMAT, okay, NEET also. So 90th percentile means that if I get 90th percentile, then out of 100 students, I have greater marks than 90% of them. So this is meaning of percentile. Similarly, it is talking about ninth decile. Don't be confused by this. In case of percentile, the sample or the data is divided into 100 parts. In case of decile, it is divided into 10 parts. So 9 out of 10 is equal to 90 out of 100. Okay. So we have to estimate the value. So it will lie somewhere here. Okay. The normal distribution curve. So because 90 percentile means that 90% of the values of the group of raw data will lie here. Okay. So 90th percentile, on the right side of this, only 10% will lie. So we have to find this value. Okay. So here we again, if we z is equal to x minus mu upon sigma. Now, what is the mistake in this? First of all, This 90% is the demonstrates an exact value which has to be standardized or normalized to the z value. Now remember when I told you to remember some of the values. Now it is easy to convert z value into p value, but not vice versa. Okay, even if you, so it comes out to be, if we convert it into the p or the probability value, 0.9%, 0.9. Okay, now if you try to find out the z value corresponding to zero point 0.9, it will be very difficult for you. It is not possible. Okay, so instead we use this. So here you can see that the z-score corresponding to zero point 0.9 is 1.282. Okay. So directly we can say that here the z value, here we can take 1.28 is equal to this x we have to find out the 90th percentile of the income, x minus 5000, which is mu upon 2000. Okay, so x we get if we multiply it, so 25600, 2560, okay, plus 5000, so x we get 7560 rupees per month. So this is the value of the ninth decile or the 90th percentile. Okay. So this involves most of the concept, almost all the concepts associated with the normal distribution function. If I have time, or if you found this lecture enlightening, I'll come up with further concepts. We'll further build upon this. We'll discuss binomial distribution, Poisson distribution, some statistical tests like t-tests, and further discuss a lot of samples how they work. So till we meet again next time, Jai Hind.